Hello, I'm Hugh Manfield and welcome to the Fluid Space Theory Lectures. Now today we're going to be talking about the expanding cosmos and what that might have to do with the velocity of an orbit of a planet around a star or a star around a galaxy. The subject of all these lectures is covered in my book, Einstein and Aliens. The appendices cover all the math and derivations, and there's a science fiction story in the first half of the book. So why do we think the universe is expanding? Well, Edwin Hubble made observations of distant galaxies and he observed that the spectrum was shifted to the red. And the best and most popular explanation for that is that space itself, or the universe, is expanding and the galaxies are being carried along with it like raisins in a loaf of rising bread dough. So the space between the galaxies is increasing, and that space, while it expands, it actually stretches the light wave so that when we see the light coming from a distant galaxy, it's shifted toward the red. And the more space that passes through, the more it's shifted. And when we plot the galaxies based on their distance, which we use a standard candle, and the velocity, they all fall pretty much on a straight line, which is known as the Hubble line. So NASA's best number at the moment for the rate of expansion is 69.8 kilometers per second per megaparsec. Now a megaparsec is about 3 million light years. So that means that two objects in space being expanded by the expansion of the universe will be moving apart at about 69.8 kilometers per second. Okay, so what does that mean for us here on Earth? Well, I calculated the expansion between the Earth and the Moon, and it's about less than a millionth of a meter per second. So that's not very much. You can probably ignore that. Between the Earth and the Sun, it's more about a third of a thousandth of a meter per second. And between the Sun and Saturn, it's about 3,000ths of a meter per second, so that's getting a little bit bigger. And between the Sun and Uranus, it's about 6,000ths of a meter per second. So that's not very fast. And we probably don't have to worry about that level of expansion in the solar system. But when we look at a galaxy, and let's just choose a galaxy that's 13,000 parsecs from the core to the galactic rim, and that'll be about an average size spiral galaxy, we see that the rim stars will be expanded away from the core at about 907 meters per second. Now that's starting to become a little bit more significant. So when we look out into our solar system, we don't really see any effect of expansion on the movements of the planets. And when we look at galaxies, we don't see stars being expanded away, and we don't see galaxies losing stars to the expansion of the universe. And observations also have shown that the expansion is accelerating. And what they tell us is that eventually expansion will become so fast that it will start to pull stars away from galaxies, and then eventually it'll pull planets away from the stars in the solar systems. And even if it gets fast enough, it could actually pull a planet apart and turn it into rubble. So my question is, when is this going to happen? Do we have to worry about this right away? What is the equation that we plug the numbers into that tell us what level of expansion is going to cause stars to drift away from galaxies or planets to drift away from stars? And I haven't been able to get a good answer to that because I don't think anyone in science is actually looking at it. So when I asked NASA, do you guys have to account for the expansion of space in calculating orbits for your spacecraft or tracking the planets? And they say no, everything obeys according to Newton's law. So they don't see any problem, and they haven't had to deal with the problem, so they haven't solved it. And when you look at cosmology, I asked the people at Princeton, since they do a lot of galaxy modeling, in your galaxy models, do you account for the expansion of space-time, the expansion of the cosmos, and they say no, all you need is plenty of dark matter and Newton's laws. So no one's really tackled the problem of what does expansion do to the orbit of a planet. Now, either it has no effect or it's not happening. But they claim that expansion will eventually pull galaxies apart. So expansion must have some sort of an effect. But I haven't found any scholarly work on the subject, so I've had to come up with my own solution. And to do that, I went back to Newton's method. Around 1665, Newton was able to calculate the orbital velocity of the moon, worked out based on his inverse distance squared gravity law. And how he did that was he assumed that when an object is traveling around an orbit from point A to point B, it's going to fall at some distance due to gravity, and at the same time it has to translate horizontally some distance to remain on the circle, and that distance is proportional to the velocity. And he used the method of equivalent triangles, knowing that the little blue triangle has the same angles and is an equivalent shape as the big yellow triangle. So he could say that s is to x as x is to 2r minus s. And he wrote that equation, and then he simplified it by saying that when s gets very small, the 2r minus s approximately equals 2r. And from that, he was able to write an equation for orbital velocity, and it can be expressed in terms of the mass of the central body or the acceleration of gravity. So thinking about this, I applied Newton's method, and then I added expanding and contracting space-time. Now, the theory then works this way. An object will fall the same distance due to normal gravity that it did before, but this time we have contracting space, so it's going to be pulled in a little bit further during that same time period, and it will have to translate a little bit farther to the side, and that equates to a higher velocity orbit. Now, on the other hand, if space is expanding, it will fall the same distance due to gravity, but then it will be expanded back outward some small distance, and it will have to travel a shorter distance to remain on the orbit, and that will equate to a reduced orbital velocity. So according to what I've worked out, expansion will slow an orbit and contraction will speed up an orbit. And the method I used is I applied a scale factor to the acceleration by adding the distance due to gravity plus the distance due to contraction divided by the distance due to gravity. And that gives me a number that's going to be 1 or greater, and I apply that to the acceleration, and that will give me the orbital velocity, including expansion or contraction. So let's see if we need to worry about expansion or contraction. I've charted how far the moon will fall toward the Earth in 1 second compared to how far cosmic expansion will expand the moon away. And the moon will fall much farther, so we don't have to worry about expansion affecting the orbit of the moon. Then we look at Earth. Earth will fall toward the sun about 0.003 of a meter, and in that same amount of time, cosmic expansion will pull the Earth about 0.003 of a meter. So that's about 10%, and maybe that's enough to notice. But the thing about gravity and expansion is they work in opposite directions. As we move out toward the outer planets, away from the sun, gravity gets weaker and weaker. But that distance is getting longer and longer, and the longer the distance, the greater the expansion rate. So when we get out to Saturn, we see that the expansion rate is larger than the distance it would fall in a second. And at Uranus, it's much larger. So it starts to bring into question whether we would see the effect on the orbit of the planets in the solar system if space is in fact expanding within our solar system. And when we look at a galaxy out at the rim at 13,000 parsecs, Hubble expansion will be expanding stars away from the galactic core at 900 meters per second. But an object out at the galactic rim is only going to fall about 8 trillionths of a meter in a second. So that's a huge difference, and it starts to get hard to see how the galaxies could actually be holding onto their stars at the present rate of expansion if it's actually happening. And I even increased the time period to 100 seconds, and we still see Hubble expansion is moving the planets away from the sun and the stars away from the core of a galaxy at a much higher rate than they would fall during that same time period. So another thing that was observed about galaxies back in the 40s and 50s, an astronomer named Vera Rubin began to measure the rotation curves of galaxies. Now, what's a rotation curve? Well, it's the rate that the stars are orbiting around the core, plotted by the distance from the core. And if you add up all the mass within the galaxy, you would expect this dotted curve to be what you see. This is the curve that they would orbit in according to Newton's laws. But what Vera discovered is that they orbit much faster, and that rate can continually increase out toward the rim. It doesn't drop off as you would expect. Some galaxies are flat, some have different rotation curves, but they're all higher and orbiting faster than predicted by Newton's laws. Now, at the same time, another astronomer named Fritz Zwicky was measuring the motions of galaxies within galaxy clusters. And he also discovered that these galaxies were moving around, orbiting within the clusters much faster than could be accounted for by Newton's laws. In fact, you'd need to have maybe sometimes hundreds of times more mass than was accounted for in the galaxies. And he coined the phrase dark matter. And people have been searching for dark matter ever since. But as of today, no dark matter detector has ever found a particle of dark matter. So the main thing to take away from this lecture is that if space is expanding or contracting, we ought to see it either speeding up in orbit if it's contracting or slowing in orbit if it's expanding. And when we look out and we don't see orbits of the planets being slowed by expansion, or we see the stars within galaxies actually moving faster than predicted by Newton, maybe expansion isn't going on locally, and maybe within galaxies, space could actually be contracting. So now that we're armed with this information, we're ready to move forward and find out what dark matter really is. And I'm going to reveal that in my next lecture. So you're going to want to join me for that. And until then, I'm Hugh Manfield.